Have you ever wondered how we can look at a bunch of data and actually predict the future with it? Well, you're in exactly the right place. Today, we're going to break down linear regression. It's one of the most fundamental tools in all of machine learning, and honestly, it's the perfect place to start. So let's just dive right in.
That's really the big question, isn't it? At its heart, machine learning is all about making smart predictions. So how do we take information from the past and use it to make really good guesses about what's going to happen next?
Let's make this super practical. Picture this. You're looking to buy a house. You know how big it is, in square feet, but how do you know if the asking price is fair? This is precisely the kind of problem we're going to solve today. So the tool that helps us solve this whole house pricing puzzle is called linear regression. And at its core, it's just a really clever way of finding the relationship between two things, like, you guessed it, a house's size and its price. Okay, so what is it, really? Well, it's a type of supervised algorithm. Now, that sounds fancy, but all it means is that we teach it by showing it a bunch of examples where we already know the right answer. Its entire job, its whole mission in life, is to look at all that data and find the one single best straight line that can cut through it to make predictions. It's all about finding that perfect line. All right, talking about it is one thing, but seeing it is where it really clicks. Let's paint a picture. Imagine we have a graph. Along the bottom, on the x-axis, we have years of experience. And going up the side, on the y-axis, we have salary. We want to see how these two are connected. Now, for the fun part, let's start putting our data on the graph. Every single dot that pops up here represents a real person with their own specific salary and years of experience. And you can already start to see a pattern emerging, can't you? It looks like the more experience someone has, the higher their salary tends to be. So we could just, try to eyeball it and draw a line that looks about right. Maybe this one? Or what about this one? Or maybe this one? It becomes pretty clear pretty fast that just guessing is not going to give us the most accurate answer. And this is where the real magic comes in. The linear regression algorithm does the hard work for us. It calculates the one single best fit line, the line that gets as close as possible to all those data points and perfectly captures the trend. Now, that line isn't just drawn at random. It's described by a surprisingly simple bit of math. And don't worry, even if you're not a math person, this is way more intuitive than it sounds. And there it is, the famous equation for a line, y equals mx plus c. You can think of this as the blueprint or the recipe that tells the computer exactly how to draw that best fit line. Let's break this down. First up, that's c. It's called the intercept. All this means is, where does our line start on the vertical axis? In our salary example, this would be the predicted salary for someone with 0 years of experience. It's our starting point. Then we have m, and that's the slope. This just tells us how steep the line is. For every single year of experience we gain, how much does the salary go up? A really steep slope means you're getting a big raise each year. A flatter slope, well, not so much. Okay, so we've got the recipe, y equals mx plus c. But how does the machine actually learn the perfect numbers for m and c? It has to figure out the perfect slope and the perfect starting point somehow, right? And this is really the most important question. I mean, there are literally an infinite number of lines it could draw. How on earth does the model know which one is the absolute best one? It all comes down to measuring its mistakes. For every single data point, the model looks at the distance between the actual dot and its prediction line. We call this the prediction error. It's basically the model saying, oops, I was off by this much for that person. And this, right here, is the heart of the learning process. The algorithm's only goal is to minimize those mistakes. It'll keep adjusting the line, tweaking the slope, shifting the intercept, just wiggling it around until it finds the one single position where the grand total of all those errors is as small as it can possibly get. So, linear regression is an amazing tool. But like any tool, it has its strengths and its weaknesses. Let's talk about where it really shines and where we might need to reach for something else. The biggest advantage is its simplicity. It's fast, it's easy to understand, and it's a fantastic starting point for almost any prediction problem. But it has its limits. For one, it assumes the relationship you're modeling is actually a straight line. It's also really sensitive to outliers. Those weird data points that are way off from the rest, they can pull the whole line out of whack. And for really complex problems, a straight line just isn't going to cut it. But don't let that simplicity make you think it isn't powerful. This thing is an absolute workhorse in the real world. It's used for everything from predicting home values and forecasting company sales to analyzing stock market trends and assessing risk in finance. It's everywhere.
And that really gets to why it's so important to understand this. Think of it as the foundation. Once you truly get linear regression, you unlock the door to understanding all the more advanced and complex models that are built on top of it. So if you only take one thing away from all of this, let it be this. Linear regression is all about finding and drawing the best possible straight line through your data to make predictions. It's really as simple and as powerful as that. So we know the model's goal is to make its mistakes as small as possible. But how does it do that? What's the mathematical engine that helps it find the best line? Well, in our next explainer, we're going to pull back the curtain on the clever process behind it all, the cost function and gradient descent. I hope you'll join me for that one.